into chapter 3, what we're going to find is here's where things really start to come together, right? In chapter 2, we talked about scalar and vector values, and we talked about how to combine forces together. So we're going to take that one step farther in chapter 3 is we're going to find equilibrium now for a particle or a point. So we're going to be combining forces together, but instead of getting a resultant force, we're going to get a resultant of 0. And then the big tool that we will use for just about the entire rest of the semester is free body diagrams, get talked about in chapter 3. So I only got a couple of slides here, but this stuff is really important, so make sure you take a look at it. So here's an example of a typical problem, 2D problem that you might see in chapter 3 or maybe some point in the future. What is it in real life? Oh, I don't know. It's, essentially what it is a weight being hung by two uh, cables. One cable is attached to the ceiling and one cable is attached to the wall. Now, we would, if that weight isn't crashing down to the floor or flying up into the air, right, it is in equilibrium, meaning there is a weight pulling down and there is a tension in the cable AD and AB, and the forces exerted by that weight pulling down and those tensions would equal 0 at point A if this thing is in static equilibrium. So things that we have to assume if it's in static equilibrium is that we're not stretching those cables, right? Those cables aren't bungee cords, they're not elastics, they're not being stretched in this particular case. So what we are ultimately going to do is, and you might think, well, it's just a problem we're doing here, but think about it. If you were going to design this system as a mechanical engineer, you would have to know what type of material to make your cables out of so that this weight doesn't stretch the cables out and the thing doesn't end up falling. I mean, you'd have to go one step farther and figure out what those anchors at point D and point B, what those should be. That's beyond this course in most cases, but you'd have to figure out what those needed to be also so that you could hang this thing from the ceiling and the wall and it doesn't come crashing down to the floor. So how are we going to do that? Well, essentially you would draw a free body diagram. So for a free body diagram, we're going to take a point or we're going to take a particle and we're going to consider all the forces that are acting upon that point or that particle and cut it out of the original system. And we're going to do that so that we can apply our equations of equilibrium. You'll see in the book and you'll see in the slides EOE for the whole rest of the semester, right? EOE is equations of equilibrium. We are going to take those equations and solve for the unknowns so that we can figure out what it is the problem's asking for. So how do we do it? So if you imagine in this particular case, we'd be doing a free body diagram a day. Now sometimes with some systems, depending upon how complex they are and how many unknowns, you might have to do this more than once. But if we consider point A and we were to look at cutting that out from its surroundings and then figuring out what forces are acting upon it, right, that's what you get. Right? There's point A on an XY plane. There are a tension going from A to D. There's a tension going from A to B. And there is a weight pulling down. So you show the forces that are acting on the point or the particle. What are the active forces that want to move the particle? Well, what's going to move the particle? You've got a weight, right, that's going to act its gravity to pull that thing down, right? The reactive forces are going to be the two cables trying to hold the thing up, and it would be holding it up if it's in static equilibrium. So the forces are identified, FD, FB, FC. Quite honestly, if I were going to draw this diagram out, I probably would have called it TB, TD, because they're tensions, and I probably would have called it W for the weight pulling down. But, again, neither is right or wrong. The directions are important, and the angles that are given in a particular problem are what's important. Now, one note on the XY plane, you can specify your XYZ in any direction you choose. Usually you want to apply it in a case where it makes the most sense. The way they've applied it here, you notice that FC only acts in the Y direction and FD only acts in the X direction, right? So the only one that you're going to have an X and a Y component associated is FB, which makes it a little bit easier. And they ask, what's this? The 392.4 newtons. Remember, we need to have weights, which is mass times gravity. So they took the 40 kilograms multiplied by the constant 9.81 meters per square second and got 392.4 newtons pulling down. Right? So now with this problem, what we could do is we could solve for the tensions in the cables, the two cables that are there. So there's our drawing again. Right, essentially what they're saying is we know this thing is in equilibrium, or we're going to assume it's in equilibrium. So that means that the forces FB, FC, and FD are equal to 0, or the sum of the forces are equal to 0 for this thing to be in equilibrium. So for that to be true, right, for all the forces to be equal to 0, the forces in the X direction would have to be equal to 0, and the forces in the Y direction would have to be equal to 0. Those are our EOE, equations of equilibrium. We could apply those two equations, E of E there, and summing the forces in the X direction, setting them equal to 0, summing the forces in the Y direction, setting them equal to 0. We would solve for the unknowns, the FB, the FC, and we know the tensions in those two cables with only knowing what the weight is that's pulling down. So we're going to write the equations. So what do we have acting in the X direction? Right, in the X direction we have a X component for the AB, and we have the D force acting in the negative X direction. What do we have acting in the Y direction? We've got the weight pulling down, negative direction, and we have a Y piece of AB pulling up in this particular case. Those are the two equations. You could use those to solve for the two forces, and we get a force in the FB force. So the force between A and B is 785 newtons, and the FD is 680 newtons. They put those little arrows on there to denote the direction. However, what's typical is you would use plus and minus signs, and typically just like you would do with a XY plot, right? To the right and up would be positive, to the left and down would be negative. So FD, and you can see, would end up giving us a negative value, and FB would end up giving us a positive value in that particular case. So there you go. That's the important parts of Chapter 3, where we're dealing of equilibrium of a particle or a point.